a programming language is for solving problems mainly. So, solving them in the most easy way possible, reusing whatever we have reusable, making it maintainable, and programming at the higher level possible. People, the people that need solutions expressed in terms of formulas and recipes. And it will be very good if we can translate those formulas and recipes as they are and make them run. Formulas are composed of functions and binary operations which combine two elements of the same kind and produce a third. And we can combine them as many times as we need. So we can create very complex components made of binary combinations of other smaller components. And it is, in principle, very good for reusability. Recipes are a sort of a very high-level sequence of steps which are not imperative. It really express the minimum sequencing possible to solve a problem. So, but we can interrupt a recipe at any moment and we can continue the next day. We can do it collaborating among many persons. We can cook a recipe with 3 or 4 persons. The recipe doesn't say nothing about the number of people. We can parallelize it. We can even go back. If we have a problem, let's start again from this point on because we have this done. For example, if some ingredient of our cooking is it's not good, we can start from a previous point. So the formulas and recipes are declarative. So that's the question. They are very description at a very high level. The question is why the code cannot be done with recipes and formulas as the people that have the problem describe it. If we look at a simple recipe, for example, how to cook a egg, you can see that we cannot even get an egg without having problems with programming from the first moment. To have an egg, maybe we have an egg in a basket that we can get one, but if we don't have eggs, we have to make it happen. So we suppose that Peter is a robot controlled by a framework, and we tell Peter to buy eggs. So we need a callback, for example, to tell the framework what to do when the egg is available. So we have a callback, a set handler to indicate to the framework what to do. So we perform the rest of the recipe when the egg is available, and so we start with the second task, which is get the pan. And all of this is programmed with no concurrency at all. And you see that the problems that we have with asynchronous communications with robots, or concurrency with the task, the Peter task, we can have, you see, interruptions. The egg can fall in the floor, and we have to begin again. What I propose is something that isolates the get egg and all the complexities in a single element that is composed with the rest of the recipe, so that we manage concurrency, exception management and callbacks, so that the get egg is isolated from the rest of the recipient and carry out everything necessary to manage the eggs, including if the egg is broken, we can start, the process can start again from the beginning with the pan, the oil, and the plate, but that we already have. You say these sentences that are the ones that we are talking about now. Well, the main problem, how many time I have, you know? How much time? 1 hour or what? 2 hours? 1 hour, okay. The problem is asynchronicity. Everything that forces us to do something asynchronously. And this, for example, events with the callbacks, routing, web request, GUI programming with events in the mouse, blocking, threading, messaging, logs. At the beginning of programming, there was no mix of I/O or with CPU processing. The first computers were pure. You know, in the film, those big tapes working, and the process was very simple. The computer, the program reads all the tape, then it processes in memory, and then generates another tape for output. So the first computers did pure processing at the beginning. When the time-sharing operating system appeared, they mix I/O with CPU processing, and that virtualization of that allows this composition of I/O and processing of the CPU work, stopping the process, executing another thread or another processes in the system, so the computer is shared among many processes and many users. And when the buffer was filled, the process was called again, so the thread continued. The price to pay for this composition, which is, let's call monadic composition, is that the process blocks the entire process. The process of I/O blocks, so nothing more can be done in this thread. That was very good for console application when you have only one keyboard, one entry, and that's fine. One thread, one user, one blocking I/O operation, and everything composed very well. Console applications are very easy to read because they follow a flow very clear, and no breaking of the flow of the code with anything asynchronous. But in the 90s appeared the mouse, which is a second source of input. So the programmers, not only the system programmers that use interruptions and messaging, had to deal with asynchronous programming, but everyone. And that is when Apple and Microsoft introduced the mouse mainly. And then the solution was the event loop. The event loop with, because there are many sources of input, to be responsible, we need many threads. Because we have many threads, we need mutable state to communicate the threads. So we have concurrency. We have a lot of state and centralized with, in the same way that now web applications are done, which are a substantial amount of state for the user sessions and things like that. So the solution was object-oriented programming. because the first object-oriented languages were specifically to deal with asynchronous messages. And in fact, the definition of object-oriented programming is object receive asynchronous messages. That's the design of Simula 1 and Smalltalk, which was I don't know if created but promoted by Xerox to deal with mouse in multi-window environments. OOP is a state object is a state machine. Many objects are many state machines that communicate among them with asynchronous messages. That is the key of object-oriented programming. Why we divide the program in different state machines? Because the state is smaller, and we can control it better, isolated with a clear interface. But the problem is that we have so many objects with different definition, different interface. Let's say that the analogy with the hardware is an OOP framework with our programming. Using it is like a custom chip with within a printed circuit. You have so many chips with different interfaces, with a complex description that you have to know very detailed to program. Our goal is a USB bus, because a serial bus specifically, because a serial bus is a common interface for all the chips with a single way to connect. We can interchange one chip with other. We can put as many chips as we like. In functional programming, the solution usually used to be continuations, but continuations are quite hard to master, and doesn't follow the laws. Any law are too powerful. So we need a new kind of continuation which follows the laws of monads, applicative and alternative. So let's look at a monad in a different way. Let's look at the bind operation, which is this, which used two different parameters. One is one computation, the other receive the result of the previous operation and then execute it. Let's look at this sequence, which is a simple sequence of actions with bind, which the sugar to this expression. And the only remarkable thing is that X is used both for the second term and for the last one. When the second bind is executed, what we have in G and what we have in F. In G we have the result of A, which has been executed, applied to B. B is not executed yet, but it has X evaluated. It has A evaluated and its result is X. So we have like a lambda expression with a value applied to it. And the second term is something that is not yet evaluated and has one parameter and execute the rest of the computation. This is clearly a continuation. But what is G? G is as depending on the engine that the interpreter of the compiler, you will see different things in G because your evaluation can be based on rewrite variables, or you can use throngs or suspensions, etc. But whatever the concrete implementation, what G has is variables that already have been executed, result of as already executed statements, and a computation that still has not been executed yet. So if we have G and F, we can, at the binding execution, the idea is store G and F in an underlying state monad. And when something asynchronous happens in G, we re-execute G and F. So we can do interesting things like as we will see now. For example, we can handle events. Let's propose one primitive called white events that apply to a blocking I/O operation will return its result and will be processed. But we will do it as many times as necessary. Every time that the blocking I/O returns something, white events will reschedule the blocking I/O operation. What will be the definition of this primitive? If we are in the underlying state monad, state which is inside our monad, we use a buffer which initially is empty. We fork a loop with the execution of the blocking I/O. Whenever the blocking I/O returns as message, we put this message in the buffer and then execute the closure and the continuation. And then to the current thread that executes this fork, we return empty. So empties stop the execution of further processing. But we have execute G and F. So G and F is again this one, all of this. So white events is executed again. When white events enter again, the buffer is filled, so it goes through this and return the buffer content, which execute the process. You see? So we have a double execution of this because we execute G also. That is very important for composition, as we will see later. So this computation, let's say how it works as real example of how this is the code that you see in the presentation. It's a white events. Read for the keyword align, and it should print this, print the result. I have this. But what is important to remark is that because this arrangement is possible, this monad can return 0, 1, or any number of results at any time. Why it can return 0? Because empty stops the execution at any moment, and in particular can stop at the first moment, so no result can beat the result. This is a IRC client made with this very same combination 2 times, one for the input and one for the output. The process is identical in both cases. We have 2 parameters. One is the input, the input channel, and the other is the output channel. So we manage input events and output events the same way. We can have different variants of event handling primitives, like similar to white events. For example, parallel white events wait for events permanently. It executes a blocking I/O computation, then reschedule it to the end. Parallel has some data definition that allows to stop doing that by an error or for indication that there is the last data or there is no more data. Async is do the asynchronous operation just one time. Sample is for non-blocking I/O. It performs a kind of polling. And abduce is nice, but is a version of async. And what it do is simply the computation continue in another thread, different thread. It do exactly the same, but in another thread. So and return empty to the current thread. So it can execute alternative computation. Very similar to the problem of overcome blocking I/O is the problem of solving event handlers without event handlers. And the solution, the structure is very similar. There is no fork, but the first parameter of this arrangement that allows the execution of event handlers. I don't know if there is a sample of use. No. The goal is this, the last line. Instead of passing of continuing the flow in an event handler, we want to receive the event in the current monadic sequence. But let's pass this because we don't have many time. You will see the structure is very similar. Another composition is applicative and monoidal. So we have arrangement of this kind which perform concurrency. Let's say an example. This is a monoid combination which has 2 asynchronous tasks, and the result is processed in a common thread, you know. This is part 2. This works as how I can see that these two threads, were it's a little bit complicated. This is the closure. Whenever one of the two results are calculated, the closure inspects the other, which is stored in a mutable variable. If the other has finished, then the thread that finished last, because the other has been finished already, execute the rest of the computation. That's the idea. And one of the two will continue, but not both. And there is no master thread. The continuation is executed by one of the two. The same happens for an applicative, because really a monolith is a kind of applicative. So we can do the same for this. Only that the result will be whatever you put in the operation. Going from applicative to one algebra is easy, because an applicative is a let's say a half-cooked algebra, because it is a binary operation. Symmetric binary operation, which unlike the monad, one do not depend on the other. So we can create numeric algebras or relational algebras with the applicative. And because the applicative handle events, handle asynchronicity, anything, you are free from effects, and you can use your formulas literally to program without concern for effects. For example, this is a simple example that uses a formula, which is very simple. The amount of money is equal to the price of the product for plus times the quantity of product sold. So we can print in real time amounts of money sold in when we connect the price with a callback. Imagine that there is a framework that calls us when the price changes. And imagine that the quantities arrive through a channel. It doesn't matter, because this formula applied here will reactively return combinations of prices and quantities, multiply them, and it will print them. You know, so we are using the very same formula that you will use in pure programming, because we have resolved the problem of events and the problem of blocking I/O. Yeah.
What's the type of the mouse? So I guess that's
the type of.
So I guess that evaluate the transient I/O double as well for the mouse.
Yeah. Amount is a multiplication of two double values. Yeah, and instead of on the I/O monad, we execute in the trans I/O monad, which is the one that handles the effects. And it's the monad that has these primitives, white events and react. One is for events, and the other is for blocking I/O. Because the applicative can manage this kind of effects and still return whenever a thread finish here or here, a new amount value is returned.
So it can be triggered basically from either of those.
Any one of the two.
Say quantity evaluates 5 times and price evaluates once. Is that basically it reuses the last price that it?
Yeah, the last price. Yes, yes, because the alternative instance is done in a way that there's the closure once the price expression returns something, it is stored in a mutable variable, and the other term of the applicative inspect the other mutable variable. If it find the last value is the value that used to apply the multiplication. It's a form of concurrency, very simple but very general. It allows a lot of complexities.
Does it reduce the complexity to become much weaker, or does it keep reduce the complexity to keep a lot of power?
Keep a lot of power, I think, yes. And in terms of type safety, it's the same. And you use exactly the same for the same pure computation that you know. Console. Let me check the work. Console input can be done also with something related with weight events, but we read a buffer, we validate it, and so we can combine. Using alternative different menu options, so we can compose different programs, different console programs that are each one waiting for the keyboard input for some input. I don't know if we can execute the sample. I think so. We have not have much time. We can also input from the command line, so we can enter very complex inputs to initialize and configure the program. Each one of the programs that might be like the composition of the whole program. Thread control is very important because we can have a very large number of threads generated with alternative combinators. So we instead in white events, instead of generate automatically a new event, we check a number of a mutable variable that contains the limit of threads. When we reach the limit, instead of executing the continuation in a new thread, we continue the current thread. So we control the number of threads. This is a primitive which is a fold of many async tasks. Each one return a value. So it's exactly the same as a list monad, which can enter different, can process using indeterminism. Only that each result is processed in a different thread. So if we don't control the number of threads, if this is 1,000, we will have 1,000 threads. This is not optimal. What we have to do is limit the threads with this primitive. This is really a loop without one thread, because we don't allow new threads. So the current thread performs all the loop, all the processing sequentially. I don't know if I think there is a sample here. Yes, this. Fine. I print also the thread. There is no limit of threads here in this case. You see that each result generates a thread. 68, 69. If we limit the threads, it's the same thread that processed every result. If we augment the number of threads, we will see that there are some threads die and another thread is created, so there is not even at the same number of the same thread identifier, but simultaneously there is only three threads. More things. Well, one thread is to kill sibling threads. Kill child, kill the sibling, the child's threads. This is a way to manage threads without using explicit pools. More. State is another another important thing to manage in any program, and it must be to program easily, and it must be very easy for the programmer to create user state and manage it. So the state in this monad is indexed by type, so each the programmer can create its own types, and the monad store this state using a map. So it's very easy to, without adding monad transformers to manage whatever state it needs at any moment. E-bars are for communicating different branches of the computation, because each branch has is running in one thread. Imagine that you have two programs, each one were running in your own side, and they have to communicate. You use a channel that communicate both. And these channels are reactive because a reactive bar is a white events that read from a channel. So each time that a bar is bright, immediately reactive bar succeeds and return to the computation this value. We can compose as many reads of the same bar, and each of the branches will receive one value of this channel. So we see that the output of this program, the numbers are repeated, because we are writing this sequence in the EVAR.
Any guarantee on sequencing that?
Sorry?
Is there any guarantee on sequencing? Are they always going to go round robin, or put one of them got?
No, because each one is a different thread. It's a different thread because White 7 is multi-thread. It's multi-threaded. You see the definition at the beginning. It performs a fork queue for each entry in the channel. It's like choose.
Yeah.
You know, choose is also defined in terms of async, which is very, very similar to white events. I don't know. This is white events. You see that there is a fork queue here, and in the current thread, for the thread in which white event is initialized, it's an empty computation. So the next, the alternative white event, which is the next, is executed also in parallel. It's a bit, but once you think in terms of threading, it's quite easy. Well, so because we have a big number of threads running, we define a way to label threads and inspecting the threads in the execution. These are primitives for state labeling and state display. If we execute this and we want to inspect the threads, we can use this. And this is the display that appears in the window. A is a task which async generate another thread which generate B task and so on. I don't know if we can see this here. Yes, you see the threads here generated in this execution. Well, many threads are finished already, but some are dead, but are presented here. We can inspect the state of the whole computation because each thread points to the thread that created it, and each thread stores the information about how the state variables were at the moment that the thread was created. So we can navigate the thread, the tree of states identified by thread identifiers. So we can see this state, this variable, this state variable, what was his value, or even modify it. For example, the limit of threads is a state variable. We can modify from a monitor the number of threads limited for a branch of execution. Exception is another reason for non-composability. This is the problem with exception is very wide, and I cannot. And there is no agreement on that, but I will show you a simple example that I hope to be self-descriptive. This is the typical problem of, for example, a web application that in which the user selects a book, then it's in the cart. And when he goes to pay, it enters a card. Then the book preemptively reserve the book. For example, let's say that. Let's think about that. Then the payment is executed, and there is a failure. There must be a failure, but if there is no failure, the order is processed. But we have some state here that we have to fix when there is a failure. Usually there is a car failure exception executed. These primitives, what they allow is to assign to each statement a car failure handler. So the car failure handler for the reserved book is just unreserved. For example, incrementing the stock of books. And for this car failure handler, the handler is ask the user for another card and continue forward. So what this primitive do? Instead of setting event handler, setting exception handler, it performs a backtracking. It executes in reverse order the handlers defined. And whatever it found continue, instead of executing more older handler, it continue executing the continuation. So we need both the handler and the continuation in the state. So let's say that we store a stack of different handlers and continuation in the state. Whenever an error occurs, we throw the error, but throw is an interpreter really. It's an interpreter that reads the stack of handlers, execute the handlers, and if the backtracking flag is on, it executes further handlers. But if there is it continue unset the backtracking handler, instead of executing more handlers, it reads the continuation and execute the continuation. So the result is that it executes until a level and execute forward from this moment on. You know, it's a navigation of the monad. And the pseudocode is not very difficult to understand. It's as I describe it. The trick is that we have the continuation. When I mean the continuation, I mean the closure and the continuation. Logging is another. Wow. Logging is another very powerful effect because we can stop at any moment the execution and continue another moment, the next day recovering the state of the computation. We have defined a very simple primitive which is logit. Logit has one parameter, and simply it reads the value return, store it in a state variable, and return its value. But if the value is already in the state, instead of executing the parameter, return the logged value. So this program will return hello instead of the execution of foo. You know, because in the log there is hello already stored. And the pseudocode is here. So we can use logging for remote execution. Why? Because we can serialize the log, we can transport the log, and the log can be read in another machine to recover the state. So we need a listen for a primitive that listen for a socket, and a primitive that transport the log, and a primitive that establish a connection with a node. There's three primitives. We need this allows to execute immediately. So this listen for a socket, but return execute immediately. So this body of the program can be invoked both for directly or as a result of receiving something by listen. And listen what received is a log. So the log is executed in the remote node, and the computation continue when there is no more log. So this is the pseudocode for wormhole and teleport. And this is a complex interaction which I don't have many time to explain. But the main idea is we compute in each machine, we transport the log. The log is read, and the computation in the remote node continue from the point of when the log is finished, you know. But we also transport something additional, and is a closure identifier. That way, when the remote node responds in another teleport, which returns his log to the calling node, instead of sending the whole log of from the beginning, it tells the calling node that this log applies to a certain closure, which is the one that has to interpret the log. And the log is much shorter because it contains only what has changed from the last teleport of the local node. So what the logs transport is the incremental, what is new, what has been done in the remote node. It seems to be complex, but it is not. Really, what a log is a root. A log is a root in web applications. Only that instead of the root being generated by the user, it is generated by the program. That's the interesting analogy, because a root contains values that are read by the program and navigate to the point where we need to execute. A log used that way is exactly the same. We can also, in this example, we are sending a string of values, because we have a choose here, which is generate 10 threads. The 10 threads are forwarded to the remote node. The remote node calculate a value for each value entered, and so there is a string going on in both directions. A string of values. So we can also a string in the reverse direction. We go to the remote node and install a wait events here. A wait events generate in the remote node many outputs that may be forwarded to the local node. So we have remote streaming this way. Or we can also move to a third node, because once we are in the second node, we can perform more teleports. RunAt is a combination of the two primitives, two teleports and nothing more. We connect with a remote node, execute this remote computation, and return the result back. So we can do exactly the same combinations using in non-remote application combination. This is a curious combination in which we have two alternative computation, and we discard the second. So we get the first result, and the other is killed. We can sequence remote computation the same way. Well, connect, initialization. Services are until now all the programs to be communicated must be the same, must have the same code. Not the same architecture, but the same code, because the routes The logs has to be understandable in both sides, but this is service allows two different, completely different programs to communicate, but still keeping properties like streaming, mainly streaming. So we can do things interesting, like for example, we can call a database service. We can send modification of our register to the service, but in the same call, the database service can string us modification of this same service, this same register. So there is a both side streaming. We string changes, and for example, the database string to us changes made by other nodes that connect with this service. In other language, in other frameworks, there will be two completely different base code for both directions. MapReduce is an application of all of these remote invocations. It's the most known framework that do MapReduce is Spark, and it's quite complicated, but at the end simple data flow processing. The idea is to distribute the 5 phases of map and reduce, so that we can manipulate in parallel very big amount of data. There is I don't have time to detail, but this is one example that count the number of words of a test, and we use the input primitive to enter a content. We distribute the content among the nodes in the available, and each node processes its own chunk and reduce the result of all the nodes in the master node, which is the node that invoke the rest and are printed. Instead of explaining, I will present a small example. Because these are two nodes. One is in Linux, is in a Docker instance. This other is in Windows. And both are execute the same program. And these are two web browsers, one connected to the Windows instance and another to the Linux instance. Both are knows the other. See, if I list the nodes, this instance node two nodes is itself and the other is the same exactly, and both communicate with executing MapReduce. I have the traits activated to show you how is the dialogue between the two nodes. If I execute the MapReduce, you see the communication. Okay. Okay, you see the result. The other also anyone can act as master. This is the result. There is, this is an example using MapReduce. Just now we will see the code, but now I want you to see how it works. This is a chat in both sides. And you see that any one of the nodes communicate with the other. This web browser sends message to this server, but this server forward to the other, and the other way around. There is another widget that display the nodes available.
How do nodes find each other?
Sorry?
How do the nodes find each other? You have to explicitly tell them?
Yeah. To initialize the node, I initialize the communication through the command line using option. I will say you in a moment. But we also can add host and port or new nodes interactively. And what more, we can display all the widgets together. The MapReduce, the chat, and the monitor nodes here too. And the code is right here. It's here. This is the this is the menu of the application. The option, the link to MapReduce, the link to chat, the link to monitor nodes, and the link to all the three widgets. You see that it's a program much like a console application, because we read the option is chosen by the user, and we, depending on the response of the user, we present one of the or the other of the widget. MapReduce is just at this area with a button. We use guard to avoid execution when it's empty. And with this sentence, we send the content to the server. And what we do in the server is this, which is print the content in the console and perform the MapReduce in all the nodes available, and then return the result to the browser. The browser, what do is to put the result in the below the input box. More interesting is the chat, which is basically the composition of two elements. One send a message, and the other receive the message. Send message is like the MapReduce box. Is a input, a word here, and add remote execution, which execute in the server the following. First, get my node, and this, perform this, which is, I didn't explain in the presentation, but what do is, in all the nodes connected, execute this. And this is putting in the mailbox of each node this information. This is send nodes, send message. Wait message, do the read of this information in each of the nodes. What do is in the server, read the mailbox and return the value. Finish.